Thank you very much for attending this session. Today I have a guest speaker. My guest speaker is Dr. Muhammad Modarres, who has his PhD from UCLA in Operations Research and who is a full professor at Sharif University of Technology, the Department of Industrial Engineering. To the best of my knowledge, the Department of Industrial Engineering of Sharif University of Technology is among top 30 finest industrial engineering departments in the globe. Today, we assume that you have been introduced in a half an hour, 1 hour, 1.5 hours to the basics of linear programming. You know what linear programming is. And then we built on it to explain several things. Even if you have not been introduced to linear programming, but you have full concentration in this talk, I think you will grasp the concept. I will also ask Dr. Modarres to provide you with an introduction to mathematical modeling and also the basics of linear programming. The problem that we discussed today is a very interesting problem. While it is simple, at the same time it is very interesting because it will give us the opportunity to formulate a linear programming model, a special case of linear programming model, which we call it the transportation model. It allows us to introduce the concept of binary 0-1 variables. It allows us to introduce the concept of integer programming, and also it will let us to introduce you to perhaps the basic model in supply chain. I assume this will be a very fine talk. I hope, and I wish. So, let's look at the problem. In this problem, we assume we have a set of production or manufacturing plants. It can be from one to whatever, but in this specific problem, we assume there are 4 manufacturing plants with a specific capacity. On the other hand, we assume that we have some distribution centers. We can have from 1 to whatever number you may wish distribution centers, but in this problem, we assume that we do have 4 distribution centers. So these manufacturing plants provide product, supply product, and these distribution centers need product, demand product. It is not necessarily to have the supply of the sources equal to the demand of the destinations, but in this problem, we assume they are equal. There will be no change in the model if they are not. One other component of this system, of this network, are warehouses. Products are not directly delivered from manufacturing centers to distribution centers. They first are delivered to warehouses, in this between, as transshipment nodes, and then they are delivered to distribution centers. In this problem, we assume we have 3 warehouses. You can have 1, 2, 3, 4, 5, whatever you like. There will be no significant changes in the problem. But we assume that the capacity of warehouses are less than the capacity or demand of distribution centers. And therefore, we need to add 1 or more warehouses to this system. The larger the number of warehouses that we need to add, the more complex the problem. The essence of this model, the essence of the formulation remains the same, but solution time could significantly go up. In this problem, we assume we just want to add 1 new warehouse. But there are 3 candidate locations for this specific warehouse. And the purpose of that warehouse is to balance the capacity of warehouses and capacity of the distribution centers and production centers. There are 3 costs involved in this problem. Construction costs, installation costs for each of these 3 candidate locations. A warehouse, 3 candidate locations. And the construction and installation costs are not the same in these 3 locations. That is one component of the total cost. The other component is transportation cost from production centers to warehouses. And the third component is transportation cost from warehouses to distribution centers. Supply of the manufacturing centers equal to demand of distribution centers. We want to add a new warehouse to make this capacity also equal to those 2 capacities. Then when this new warehouse is added, we want to know what is the optimal plant to warehouse transportation and what is the optimal warehouse to distribution transportation. And when we add all these things, we want to know which one of these 3 candidates leads to lower cost, lower total cost. Indeed, while in operations research models, it really doesn't matter if you write the objective function as minimization of total cost or maximization of total revenue. Philosophically, looking into the problem, I always recommend to write your objective function, if possible, in maximization form, not in minimization. In increasing the throughput, increasing the revenue, not decreasing the cost. Why? Because, and I have learned this from theory of constraint and Goldratt philosophy. Cost work is limited. What is the maximum you can do in cost work? To reduce the cost to 0. You cannot do better than that. So it's a limit for it. But what about the throughput work? What about the revenue work? There is no limitation. Absolutely no limitation. Power of production has no limitations, but cost work is limited. Second, suppose we reduce the costs to zero. What that means? It means that we have fired a group of people. And if we fire those people, other companies also find a way to reduce their cost to zero. Also, they fire their employees. And when all employees are fired, who wants to purchase our products? Therefore, while in this model we will discuss minimization of total cost, whenever possible, look the other way. Instead of trying to shrink the costs, try to maximize the revenues, to increase revenues, increase throughput. I think that is what the theory of constraints brings to the table of linear programming. So, we have three candidates. Construction costs, initial investment costs are known for these three locations, and they are not equal. Supply of each production center is known. Demand of the warehouses are known. They should match with each other. Indeed, in the transportation model, in recent years, it doesn't matter if they are equal or not, if the supply and demands are equal to each other. We can still formulate the problem. But in this specific problem, we add this new warehouse just to fill the gap between capacity of warehouses and capacity of the production center. So we have capacity of each of these four warehouses, which are not equal to each other. We have production capacity of these four manufacturing plants. And we know the unit cost of moving one unit of product. This can be one pallet, it can be one truck, it can be one 20-feet container. 20-feet containers are called TEUs, 20 equivalent units. So when I say one product, I don't mean one single product. One pallet, one container, and so on and so forth. We know the transportation cost of one unit of product from production centers to warehouses. And then we need to find out what is the best distribution from which production center to which warehouse. We have three existing warehouses. Each time we put one of the candidate locations and find the best transportation plan. Then we take this one and place the next one. Then we take this one out and place the third one. And we find three total costs for transportation from production centers to warehouses. We do the same for warehouses and distribution centers. We do have the unit cost for each origin to each destination. And we know the total capacities of here and there. And then we need to find the best plan to minimize the cost. Each time we place one of the warehouses. Finally, we have installation cost, transportation cost from manufacturing plants, transportation cost to distribution centers. We add them for each of the three locations, and then we select the location which leads to minimum cost. After solving the problem in a linear programming form, so that requires solving 6 problems, then we will go and develop an integer programming model to solve it in one step.